periodic table is a listing of all the known elements. How many known elements are there? Just over 100. You'll hear in the news periodically of the discovery of a new element. That's likely one of these heavier elements located around here in the periodic table. As it turns out, these super heavy elements are so highly unstable that they exist for only a fraction of a second. These are all synthesized in the laboratory. You won't find any of these occurring in nature. The heaviest element that occurs in nature in any appreciable amounts is uranium, right here, number 92. That's right, the periodic table lists the elements by their atomic number, which you'll recall is the count of the number of protons in the nucleus of each atom. Hydrogen has 1 proton, so it's number 1. Helium has 2 protons, so it's number 2, and so forth. There are 3 types of elements: metals, nonmetals, and the metalloids, which have both metallic and nonmetallic properties. As you can see, most elements of the periodic table are metals. They're grouped here naturally toward the left side. The fewer nonmetals are grouped to the upper right, and, as is fitting, the metalloids fall right in between the metals and nonmetals. On some periodic tables, you'll see a staircase bold line that divides the metals from the nonmetals. All the metalloids hover adjacent to this staircase bold line. But because there's a gradual shift from metals to nonmetals, I prefer this view. You know, metals are great at conducting electricity. With few exceptions, nonmetals are just the opposite. They tend to be good insulators of electricity. An exception are the carbon-based nanotubes or the nanosheets made of graphene, which is all the rage now in the field of nanotechnology. The metalloids only sort of conduct electricity, which is to say they're semiconductors. The most famous semiconductor of them all is silicon. A vertical column in the periodic table is called an atomic group, or sometimes an atomic family. Elements within the same group, or family, share similar physical and chemical properties. All the group 18 elements, for example, they're inert gases. We call these the noble gases. The group 17 elements all tend to form salts, such as sodium fluoride, which, in small amounts, is good for your teeth. Or sodium chloride, found in table salt. There's sodium bromide, you'll find plenty of that in our oceans. And sodium iodide, which is what they add to iodized table salt. You see, the small amount of iodine helps prevent a medical condition called goiter, which is a growth in the thyroid gland. So elements above and below one another, they share similar properties. Take note of group 11. This is where you'll find the precious metals gold, silver, and copper. So it's no coincidence that they appear directly above and below each other in the periodic table. We say they're in the same atomic group, or family. A horizontal row is called an atomic period. Across the horizontal row, there's a gradual change in some property of the elements. The one I like to talk about most is atomic size. Atoms to the left tend to be larger than atoms toward the right. We call this a periodic trend, and it works up and down vertical columns too. Atoms at the bottom of a group tend to be larger. Putting it all together, we see that atoms of elements to the lower left of the periodic table, they're the largest atoms. Those to the upper right, they're the smallest. So let's do a test. Which is larger, a nickel atom or a tantalum atom? Look, there's no need to memorize anything. Just look. You'll see nickel is closer to the upper right, so it's likely the smaller of the two. And it is. There are 7 periods. Notice the first period only has 2 elements, hydrogen and helium. The second period has 8 elements, lithium through neon. There are also 8 elements, in the third period. The fourth and fifth periods, well, they each have 18 elements, while the sixth and seventh periods each have 32. Well, it's theorized that the seventh period should have 32. It's just that not all of them have yet been discovered. And what's this lower box all about? And these are the lanthanides and actinides. They are, if you will, subsets of the 6th and 7th periods. Technically, they should be squeezed into these periods like this. But then the periodic table doesn't fit very well within a regular sheet of paper or your computer screen. That's why they're drawn below the main body of the periodic table. The 6th period lanthanides, they're fascinating. In fact, I can show you some in action right now. Are you looking at an LED digital screen? Well, the colors you see are being generated by lanthanides within the LED. The actinides are all radioactive elements. Later we'll be discussing the concept of radioactivity and also nuclear energy. Right now, I should tell you, most nuclear energy is generated by the fission of isotopes of uranium and plutonium. Here, these are actinides. But there's much promise in the first actinide, which is thorium. You really need to learn about thorium nuclear reactors. They offer a much more efficient, safe, and environmentally friendly means of nuclear energy. We'll discuss thorium reactors later. I should mention how blocks of elements have traditional names, as shown here. The transition metals, for example, they transition from one side of the periodic table to the other. The lanthanides and actinides, they're collectively called the inner transition metals. Now, I'm confident your instructor won't ask you to memorize the periodic table, but he or she may want you to become familiar with the names of these blocks. Why? For communication. That way you won't get lost if someone ever asks you, what's your favorite transition metal? For now, the task at hand is becoming familiar with the basic organization of the periodic table. Please, don't spend your valuable time and energy memorizing this chart of the elements. Instead, focus on its remarkable organization. I should underscore, the periodic table is nothing we humans invented. Rather, it's a natural organization of the elements that we discovered. You could travel to a distant civilization in a distant galaxy, and you'll likely find a similar organization of the elements posted on the walls of their chemistry classes. Think about that. And good chemistry to you.